For a while now, Apple has been using a very special type of thermal paste on many of the devices they manufacture. If you've ever taken apart an A1932 MacBook Air or maybe even an M1 MacBook Air or MacBook Pro, you would have seen this thermal paste. It is this very, very thick, gritty, black thermal compound that you just can't find on the market no matter where you look. Now, they use this paste for a few reasons, and one of the reasons is that the heat sinks on the devices that this is used on are simply too big for standard viscosity thermal compounds. And you could easily see this when you apply, let's say, like Arctic Silver 5 or Arctic MX4 on an A1932 or A2179, you'll see that the paste just doesn't spread out very well. And we're going to demonstrate that here. So, here we have an A2179 MacBook Air board here, and this has Arctic MX4 on it. Now, Arctic MX4 is a great product when used in proper applications. Now, Arctic MX4 and pretty much 99% of other thermal pastes on the market are simply too thin for the big heatsink gaps on these devices. So, we're going to test this in a couple ways here. So, the first things first, I'm just going to lightly grip the heatsink here. Turn my microscope off so you can see the board. So I'm just going to lightly grip the heatsink off, and I'm just going to lift it off. And you could see that there was like zero effort in taking that off. And if you've ever built a PC or ever worked on a computer, anytime you take that heatsink off, you notice that there's like a seal on it. It's kind of like a vacuum that it should have some force to take off. And in this case here, it just came right off. There was zero seal on it whatsoever. And what that tells us is that the heatsink was actually not touching our processor. If it was squished down onto that thermal compound, it would have created a little bit of a vacuum, and it would have given us at least a little bit of resistance. Now, let's actually have a look at this heatsink and the CPU under the microscope and see what we find. And here we have our CPU that was repasted with Arctic MX4. And there's a few things to point out here. Now, the most obvious is that there's a large portion of the CPU die that is totally uncovered with thermal paste. And second of all, when we applied this paste, we used a line down the center and a line down the PCH, okay? And we actually used quite a bit. Normally you would use less than this. This was much larger amount than that you should actually need to cover a CPU die. And what you can see is that the thermal paste here, we could still make out the line that we applied it on. So this thermal paste was never fully squished down across that CPU, and hence it did not make a seal, and it is not making thermal contact in many areas. Now, when you apply pressure on something, it is going to flow outward, and that's what happened here. So putting that heatsink on did apply some pressure to the CPU, and it did spread the thermal compound out somewhat. However, towards the edges here, it is most likely not going to be making contact. And the point of maximum contact is going to be where this thick blob is, all right? And that's pretty much going to be the only outlet where the heat has on the CPU if you use a thin thermal compound like this. Now, spread patterns can vary based brand to brand, but most of the off-the-shelf thermal compounds will result in something similar to like this. You'll see a little thick line down the center of where you apply it, meaning that it wasn't fully squished out and the heatsink was not making full contact. We can see the same thing if we look at our heatsink here. We could still see our application line that we put on the CPU, and same thing right here. So the paste was making somewhat contact, but it was not contacting the die fully whatsoever, and this is not a good thing. So usually on a lot of CPUs, now I don't know where the CPU cores are located on the die of this particular CPU, but oftentimes on Intel CPUs, they sit on the outside. Okay, now areas that we just see plain die, those are areas that have zero heatsink contact, zero thermal compound contact. There's simply nothing there to transfer the heat off of it. So in order for heat to be pulled out of this section of the chip, it would have to migrate towards the center and then be pulled out by the heatsink. And when you have that large of a gap with the thermal compound, the contact just really isn't sufficient to pull a lot of heat out of the CPU. Okay, now die hotspots are really not a good thing, okay, because without heatsink contact, you're going to have portions of this die that are going to get very hot very fast. Now, the thermal sensors on CPUs are usually located in the processor core. There is a few other ones on the CPU, but the thermal readings do not necessarily reflect the total temperature readings of the chip. You can have areas of the chip that are getting much hotter, and you may not see that in software because of the location of the sensors. So die hotspots like this are very bad. Okay, there's zero cooling on this part of the CPU. It can lead to reliability issues as well because the expansion rate of an area that's hotter is going to be different than an area that is colder, of course. So you can have some parts of the die that are expanding and contracting a little bit quicker than other parts or slower than other parts, and that can lead to issues over time. For example, the substrate on the chip is definitely not going to like that, and that can lead to reliability issues over time. Die hotspots are something that you want to avoid altogether if you can. So normally in an application like this, we would use a thermal pad. However, this gap is just slightly too small for a thermal pad, okay? You can use a thermal pad, and don't get me wrong, using a thermal pad is far, far, far greater or far better than using a thin thermal paste like this. You might not get the best performance out of a thermal pad, but at least there'll be uniform heat transfer, and it'll be better on the chip long term. But thermal pads are kind of a pain to cut each time to length, and just using a paste is easier. So after many months of research and development and many months of testing something, we have developed our own thermal compound for these devices. This thermal compound is called carbon black. It does not contain the material carbon black, just the name of it. But this thermal compound is specifically for the Apple devices that have that large heatsink gap that use that black thermal paste. Now, before we get too far ahead, I need to put a little disclaimer here. This thermal compound is not for every device. It is not for every MacBook. It is only designed on devices that have a very large heatsink gap, such as the A1932 MacBook Pros, A1534 MacBook Airs, A1932 MacBooks, A2179 MacBook Airs, and the RAM portion of the new M1 processors. Now, the M1 processors actually use this same paste as well on the RAM portion. Not on the main CPU portion, but on the RAM portion. And the RAM portion on those chips is very much like this. They have a very large gap, and not much can take the gap away except a very thick thermal compound. So remember back when I did the test on the heatsink seal test? Let's go ahead and try with our thermal paste and see what difference it makes. And one thing to point out here, generally using more thermal compound on any of these devices that utilize a special type of paste is better than using too less. Our syringes have a specific size applicator on them, and it will not really allow you to put too little thermal paste on it. Too much is generally not an issue, but too little can definitely be an issue. So to keep things consistent, we're going to apply this paste in the exact same way. And I got a little bit too much on here. There's like a little air gap in here, so I'm going to wipe this off. I don't want this test to be biased in any way towards our product or another product, so I want to keep this consistent and fair as possible. So I am just going to apply a line down the center of the chip, just like we did with MX4. And a little line down the center of the PCH die. Okay, and that is the proper amount to put on. Generally with this applicator on the syringe, you just have to squeeze a little bit will come out, and just drag that along the CPU die, and you'll get the perfect amount on. You won't get too much and you won't get too little. You don't want a big glob on there, but you should have enough. And what that's going to look like is something like this, okay? This is the recommended application amount and method on any of the 2-die CPUs on any of these devices. So let's go ahead and put our heatsink on. I'm not going to screw it down or anything. On a lot of devices, you really have to get that pressure in to get a seal. I'm going to try it without. So what I'm going to do is just push this heatsink down on the CPU right here. Okay, so it's down. And I'm going to try and remove this. Now remember, if our heatsink is making a good contact with our chip, it's going to be kind of hard to remove. It's going to have a seal. And as you can see, I am picking it up by the heatsink. Prior, it was so easy to just pull it off, and as you can see here, I am actually holding the device by the heatsink, and it is not coming off, and that means we have a very good seal there. Okay, I could hold this upside down wherever, it's not going to come off. I'm just holding my hand here just in case, but we have a very good seal here. Now, this seal actually gets a little bit greater over time. This thermal paste is going to go through some viscosity changes when it first heats up. So at first run, the paste viscosity is going to change a little bit, and actually maximum thermal performance is going to happen after the CPU hits its temperature limit a few times, which should, on any of these Apple devices, will probably happen within the first 15 minutes of use. After those viscosity changes takes place, the paste thickens a little bit, and during this time when the viscosity is changing, the finer particles of the paste find their ways into the smaller crevices on that heatsink, and the bigger particles will also fill in those larger gaps. So let's go ahead and actually take this heatsink off and see what this paste looks like. So you will notice that it'll take a little bit of force. So I'm putting my fingernail here, and it finally just came off. Now let's go ahead and take a look at the type of spread pattern this paste has compared to what you saw with MX4 or many other similar type viscosity thermal pastes. And this is something that we're definitely proud of because it did take a lot of research and development to get a paste to do this while still maintaining good thermal contact. So you can see here that the coverage is just much greater than MX4. Now I did mention it is better to use more paste than not enough. You can see here that we still have a little bit of right here that it didn't spread out all the way. That's fine. It's not like before. And a little corner isn't going to do anything. That's why we kind of used a big applicator on our paste syringes, and we kind of recommend people to use a little bit more than you think you need, just so that your die is fully covered. But you can see here that the coverage is just vastly different. There's about 99% of the die is covered, and another thing you see, the paste totally spread out. Okay, there's no section in the center of it, okay, where there was a line. It totally spread out. Okay, with the MX4 you can see that there was a line down each die. Okay, we just don't see that here. The paste totally spread out. It totally coated the die, and there's a nice thin layer of thermal compound there that will allow for uniform heat transfer. Now this paste does provide a really exceptional heatsink seal, and when you have a really good heatsink seal, you're just going to get better thermal conductivity like that. Same thing here on the heatsink. Okay, looks good. It's all spread out. And it looks very good. Now, if you've ever looked at the apple paste under the microscope, you'll see that it's filled with tiny spherical-like balls, and you can see that our paste has something similar as well. However, we did add less of that ingredient for a good reason, though. We did want to maintain good spreadability with this, okay? And when you have something that's too thick, it kind of gets hard to push out of the syringe, and that's not something we want. Okay, this paste still allows the very similar performance. It allows the big particles to take up the big gaps and the small particles to take up the small imperfections in the heatsink, just like the apple paste does. Now, not all heatsinks are perfect. Sometimes you could have heatsinks with manufacturing defects that are slightly twisted or slightly warped. That's something that can just happen. It is copper or aluminum. Aluminum has a tendency to warp. And our next test is going to help figure out which paste can deliver the most protection in the event that a heatsink has some slight warpage. So for this test, what we are going to do, we are going to place a small amount of carbon black and MX4 on our spudger tool right here, and we're going to drag it across the heatsink at a angle about like this, so about a 45-degree angle. Now, we have used this heatsink in previous testing during research and development, so you can see some previous scar marks on it. So first off, we're going to apply a little bit of MX4 on the syringe. Now, for consistency's sake, I'm going to show you guys the amount that I'm putting on. All right, so we have a decent amount on here, and what I am going to do is hold the spudger about like so, and we are going to drag it down the center of the heatsink, and you can see here that it did not adequately spread, and we do have an area that the thermal compound was completely scraped off there. Now, this test obviously does not simulate operating conditions perfectly, but it does give you an idea of what may happen if your heatsink does have some warpage or some imperfection that it is not sitting totally flat on the heatsink. Having a gap like that can lead to small pockets of air, which of course are going to degrade thermal performance. Now again, I'm going to show you guys how much thermal compound I'm applying. I don't want the test to be biased in any way to our product or other companies' products. So I'm going to apply a similar amount of paste on here, about as consistent as I can get it, because the syringe openings are a bit different between the two syringes. And I'm going to hold this at the same angle, and I am going to squeeze this paste down the center of it. And you can see it kind of picked up there. because the stuff is so thick, so thick and sticky. But you can see that the spread pattern was more consistent and there's overall less air gaps here. Okay, so for consistency's sake, I'm going to do both pastes twice. So I'm going to do carbon black one more time, and then I'm going to switch to MX4 one final time and see how that performs. But the spread pattern was overall more consistent with carbon black. And here's the amount of thermal compound I used again. And we are going to perform this test in the same fashion. I'm going to hold the heatsink at a little bit of a 45-degree angle or so, and I am going to spread it across the heatsink. And you could see that the heatsink is adequately covered. You can see some areas where it got a little bit thinner. That is expected because, again, what we're trying to simulate is if the heatsink has a warp in it and the spudger is not perfect and it has the perfect little rough edge to kind of simulate that. You can see here that the heatsink was totally covered, and if we look down into those crevices, we can see all the unique particle sizes that this paste has, and you could see that those gaps and those little crevices are adequately filled. So the smaller nano-sized particles in this paste are going to adequately fill the smaller gaps, while the big particles take up that large heatsink gap there for maximum thermal conductivity. So again, like I said, I'm going to do both pastes twice. Let's go ahead and switch to MX4 and see which result we get with MX4 again. Okay, we have our heatsink cleaned off. We have our spudger cleaned off. Let's go ahead and apply a similar amount of MX4 to our spudger. I want to show you guys everything. I don't want something to be biased, as I've said many times. And I'm going to hold the heatsink at an angle. The spudger at an angle, around the same angle I used before. And I'm going to spread it out. And you could see that the paste did not adequately fill those gaps here, and it was able to be pushed away. Now again, as I've said many times, this does not perfectly simulate operating conditions, but it does kind of give us an idea of what might happen if our heatsink has a manufacturing defect in it. So let's go ahead and move on to our next demonstration. So one of everybody's questions is, will the thermal compound dry out? Now, the answer to that is a little bit complicated. Now, almost all silicone pastes will slightly harden over time, and carbon black is not an exception. And pretty much any any type of thermal paste that is based off of silicone will undergo viscosity changes in use, and over time it will kind of get a little bit thicker. Now, this thicker type thermal paste, after it's been in use, is not considered drying out. It is simply cured. It does not have any performance differences to new paste or anything like that, so that is not a concern. Some people see cured silicone paste and think it's dried out when it technically isn't. What you don't want to see is crackage, or if you take off the heatsink and a big, hardened piece of silicone comes off. That is bad, and carbon black, that will not happen to this paste. So here we have a heatsink here that was heated to over 3 times what the paste will see in operation of a MacBook, and we're going to take a look at its consistency. So this heatsink here was heated to around 300 Celsius for around 10 minutes. Now that far exceeds the type of use that's ever going to get seen in a MacBook, and if the paste was going to dry out, it would have shown on that test. And we're going to show if there's any separation here and what the paste overall looks like after being exposed to those kind of temperatures. Now, a lot of thermal paste, especially like the high-end enthusiast thermal grease, not MX4, but some other ones, start to degrade fairly quickly at higher temperatures. Like around 80 Celsius, they start to harden and degrade and possibly crack. Cracks you really don't want to have in thermal compound because dust and other contaminants can work their way in there, kind of get up over it, and that can seriously impact thermal transfer. So let's go ahead and have a look at what this paste looks like after a really extreme durability test. So let's switch over to here and let's have a look. So again, this paste was exposed to extremely high temperatures, around 300 Celsius. That's around 3 times what the CPU is going to get to in use. And you can see that it is not dried out. It is still very pliable. You could still see that there's a good amount of silicone filler in here. I still have MX4 in my syringe. All right, but this is not dried out. Okay, this is still very much movable, and the consistency is pretty much like new. Now, I know you guys, or somebody watching this, is not going to believe it and think that I just spread new thermal compound on the syringe. So I am going to get my hot air gun, and I'm not going to set my hot air gun to 300 Celsius. I'm going to set my hot air gun to the maximum temperature of 500 degrees Celsius. And we're going to turn our airflow down a little bit, and we are going to let this get hot. And we're going to heat this thermal paste at 500 Celsius to show you what reacts even under extreme temperatures. Now, no one is going to have a MacBook that gets this hot. No one's going to have a MacBook that gets to 500 Celsius. If you have a MacBook that's getting to 500 Celsius, you will probably have other concerns other than if your thermal compound is drying out. So what you are seeing here is the expansion of certain particles in the paste. Now, that's why you're seeing the oil kind of come to the surface here. This is a much exaggerated and much accelerated process to what's going to happen in the early stages of the paste. But basically what's happening is the smaller particles are kind of working their way into other sections of the paste and the heatsink, and that's displacing some of the filler oil, and that's why you see that oil coming to the surface there. Now, in normal operation, you're not really going to get separation like this, although it is normal over time for some of this oil to kind of weep out and be present at the edges of the compound. That's totally normal. That does not indicate the paste is separating or anything like that. That's just something that happens with almost all silicone compounds. So I'm heating this heatsink enough that it is bubbling up my mat here. Alright, this is under extreme temperatures, 500 degrees Celsius. I'm hitting the button up on my hot air gun. It does not go up any further. Let's go ahead while it's hot, have a look at the viscosity of this. Okay, see how it is thinner, and that is normal. And that's kind of what you want, because when it gets hot, it does kind of find its way into those smaller crevices, and that's not something a lot of other pastes do. A lot of other pastes are the same viscosity at really cold and really hot temperatures, and by allowing the paste to kind of change viscosity, it allows those particles to kind of work their way up into that heatsink for maximum thermal conductivity, and that's what you want on a heatsink with a big gap like that. So that is that demonstration, and we're going to pretty much wrap it up here very shortly. Now, one of the other concerns that everybody has is thermal compound conductive? And as a technician, I've seen it multiple times. I've seen it with Arctic Silver. I've seen it with the Apple Original paste. The Apple Original paste uses aluminum as a filler. I've seen thermal compound under CPUs all over the board, and let me tell you, if you have a little thermal compound on a signal line between a critical signal line on the CPU, that will cause issues. All right, if the thermal compound is at all capacitive or at all conductive, and you get a little bit between the right signal line, you will have issues here. So this thermal compound, it can be used in any application that Apple uses their proprietary black thermal paste. Now, one of these applications is the iPhones that have sandwich boards that actually use the board as a heatsink, so the thermal compound directly touches the CPU, or the thermal compound directly touches components on the board, and that, as a technician, that's kind of concerning, especially with the prevalence of some thermal compounds that are conductive. So here we have a MacBook Air that we have plastered carbon black over the most sensitive areas of the board possible. So when you're thinking about, is a thermal compound conductive, you're not really thinking about, let's say, a power rail or something. You're thinking about high-speed data lines, EDP, LVDS, CPU, SATA, PCIe, any data lines like that that are exposed to a conductive material can have crosstalk, and that can cause serious issues. So I'm going to show you where I've applied this thermal compound. Actually, I'm going to show you that this is a beautiful working MacBook Air. Okay, it is booted into our test disk. We are going to enter our password, super secure 1234, to get into our test disk, and you can see that this is going to enter our test disk just fine. This is a 2012 MacBook Air, so it is a little bit slow, but we're booted into the operating system. We are working just fine. Everything is good. So let's go ahead and look at where this thermal compound was applied now on this board. So this was applied to the absolute most sensitive circuits in the whole device. So let's go ahead and go over those. So the first one on our list is going to be the Jtag connector. Now, if anybody's watched this channel or many of the other repair channels on YouTube, what you will see is that if the Jtag connector has any amount of liquid on it, it will cause issues. And furthermore, if you have any amount of a conductive compound on it, it will cause issues. And we could see here that we have thermal compound plastered all over it, and it is not causing any issues. It still boots, it still works with no stability issues. Furthermore, our LVDS area, plastered with thermal compound. Now, our LVDS area uses high-speed data lines. Now, anytime you have any form of interference over a high-speed data line, you're going to get stuff like video distortion, no image, anything like that. And that's just not happening. You could see our image on the screen was nice and crisp and no issues. And this area is going to be kind of like a Jtag connector that's not present on the board for our PCH, which handles many PCIe functions, SSD functions. It also has the memory controller in it. And you could see that there's no apparent issues from any kind of, conductivity issues. And lastly, here is our CPU, Jtag and diagnostic port. Same thing, thermal compound all over it with no issues present. Most thermal pastes do contain some electrically conductive materials. Carbon black is no exception. However, what matters is your formula. If you don't have your formula right, it can be conductive. In this case, we worked extensively to ensure that this formula was not electrically conductive while maintaining very good thermal conductivity. And that's where we're going to talk about our next portion of this thermal compound. Right over here I have a 2018 MacBook Air that we have repasted with carbon black. And we run benchmarks dozens upon dozens of times. And what you will see from this device is it actually benchmarks consistently higher than many other thermal pastes used. What you will see with MX4 and other thermal compounds, you may still score around 1600 on multi-core, but on single core, you're going to score at times in the 600s, 700s, 800s. It's not consistent. With carbon black, what we found in our testing is it provided very, very consistent single core and multi-core performance. Now, when you're using one of the dual core mobile devices like this right here, what's going to matter most is that short burst TDP that's mostly going to be reflected in single core scores. For example, if you take a look at all the graphing and everything in, let's say, Intel Power Gadget, you will see that when the CPU is using higher wattage, okay, so if it's boosted up to 14, 15 watts, even 12 or 13 watts, you'll see that it's typically doing that on a single core, or it's raising the frequency of a single core much higher than the other core. And that is more indicative that the CPU is seeing it as active thermal headroom. Now, these CPUs do run hot. If they see their thermal headroom, they're going to increase their frequency, and it is not uncommon to see 100 degrees Celsius on any of these Intel mobile CPUs. Totally expected, totally normal. So single core scores, higher single core scores generally mean the CPU sees more thermal headroom compared to, let's say, a higher multi-core score with a lower single core score on this series of Intel CPU, not necessarily on other devices. So in our testing, we verified extensively that our single core scores were very consistent as far as numbers go. And you could see this if you look at let's say the chart. Let's just look at Geekbench, for example. We're going to use our same test device. So I just pulled up a page from a long time ago. This looks like it's from 2019, so a long time ago. And what you'll see is you'll have scores in the 700s. Okay, we have 709, 1369, 890, 1724. 770, 774, 765, 865, 815, 771, 711, 683, 819. Okay, it's off the charts. Okay, it varies so much, and what we really went for is consistent performance. I mean, that's what's going to matter. What matters more than, let's say, having a super high thermal conductivity is consistency. Okay. when you score consistence in the high 800s, you know the thermal compound is doing a good job, and that's what we care about. We care about consistency. We care about uniform heat transfer. You could have a thermal compound that is really, really high thermal conductivity, but if it doesn't provide uniform heat transfer and does not contact that die fully, that is going to be so much worse than, let's say, a thermal paste that has lower thermal conductivity but contacts the die properly. Now, some of you guys are probably thinking, well, this stuff sounds great. I'm going to repaste my personal laptop, my AMD Ryzen desktop, my PS4, whatever with this paste. No, okay? This is a specific design product for devices that use Apple's very thick black thermal compound, okay? If you take apart an Apple device, you see it has the black thick thermal compound, this is the paste for you. If you take apart an Apple device and see that it has a standard gray thermal compound, do not use this. Use a gray thermal compound. Now, we currently do have a regular type thermal compound in development. I'm not going to say too much about it right now, but stay tuned for an official announcement on that. But if you use a too thick thermal compound with big particles like this on something that has a very narrow heatsink gap, you're going to have thermal issues, and that's not what you want, of course. Okay, similar to how if you use too thin of a thermal compound, like on these devices, not particularly this MacBook Air, but all the other MacBook Airs, the newer MacBook Airs, you will have thermal issues as well. So this is a specific thermal compound to solve a problem. There's nothing else on the market that can provide this is good heat transfer, is good heat thermal contact that this paste does currently, and that's why we created it. You know, we see a lot of devices here, and it just felt, you know, inadequate to not be, you know, replacing the thermal compound properly after, let's say, board rework, and that's why we created this thermal compound. Now, something else, this paste is solely, fully, and completely designed and manufactured in this building here. It is not made in China. It is not outsourced to some other company that's making it. It was not designed by some other company. I designed this thermal compound. It is fully 100% manufactured in the US in this office here, and we do not have any plans to change that, no matter how big this business may get as far as the manufacturing thermal compound. So to buy this, there's a link in the description. The website is now live for this paste, or I should say the page on our website is now live. Now, through us personally, we are only offering domestic shipping at this time via UPS. However, you will have international availability and US availability, of course, through Injured Gadgets very soon. I will definitely update the description and the link in the comments below with a product page to Injured Gadgets paste that they're going to have up there, which is obviously our paste. But I will definitely update that as soon as it becomes available. But for the meantime, if you want to pick up a tube, go ahead and click the link in the description, follow the website, and you will be able to purchase this paste and use it on any devices that may come into your own shop or your own MacBook Air if, let's say, you repasted it with something a little bit thinner.